Dear students, in this video on work, energy and power, we will study work done, power with some numerical examples. So let us begin with the idea of work done in physics. So see, you have an object placed on a surface and a force F is applied on it and it undergoes some displacement S. So, when the force applied on a body produces displacement along the direction of the force, work is said to be done. Now, if the force is along this direction, like this, work is said to be done. But what if the force is not along the direction of displacement? If there is some angle between them, a general case, then the amount of work done is given by scalar product of force and displacement. So we look for a component of force along the direction of the displacement, and if this angle is theta, that component will be F cos theta. So F cos theta multiplied by S. F cos theta multiplied by S. Or we can say that work is given by scalar product of force and displacement. Force or displacement दोनों vectors हैं, but work is a scalar quantity, right? So now theta is angle between F and S. The SI unit of work done is joule. Dimension of work done is ml2t minus 2. Some special cases. Now, when force is not 0 but displacement is 0, then the work done will be 0 according to this relation. So, it is something like if you try to push a wall by applying some force F, displacement S is 0, so no work is done. Even though you get tired, no work is done. Now, some special cases. For parallel vectors, when force and displacement are parallel, that is, the angle between them is 0, and you know that cos 0 has maximum value equal to 1. So, if a force and displacement are parallel, like applied on this body, then in this case, when displacement takes place along the direction of applied force, the work done is simply F dot S or Fs, which is the maximum work done by given force. And now, when the force and displacement are anti-parallel, that is, angle between force and displacement is 180 degree, and you know that cos 180 degree is minus 1. So, if the force and displacement are anti-parallel, like a familiar case is that of frictional force. So, if the displacement is along right direction, the frictional force will be opposing it. So, this is displacement, this is frictional force. See here, the angle between force and friction is 180 degree. So, the work done here is F dot S or Fs cos 180 degree, that is minus Fs. So, work done is negative in this case. So, work done by frictional force is negative. So, the work done can be negative, can be positive, can be 0. It can have any sign. And what if the vectors are perpendicular? That means if force and displacement are perpendicular. You see, if theta is 90 degree, cos 90 is 0. So, you know that scalar product of two perpendicular vectors A dot B is 0 because cos 90 is 0. So, when the force and displacement are perpendicular, work done will be 0. And a very familiar example can be that of Cooli. You are familiar with this example. See, when a coolie carries a box on his head and moves on a platform, he applies force in upward direction and displacement is in horizontal direction. So the work done by him is 0. See, this coolie is carrying a box on his head. See, okay, here. Now, he is applying force in upward direction. Displacement is in horizontal direction. Angle between them is 90 degree. See, displacement is not 0. Force is also not 0. But work done W is 0 because force and displacement are perpendicular. So a very important point to note here. And now another known case to you is circular motion. So let us see what happens in circular motion. So you know that the force in circular motion is towards the center. It is called centripetal force. So force is acting towards the center and displacement is always along the tangent. So if the particle lies here, the displacement will be along this direction, force will be towards the center. If the particle is at this position, displacement will be along the tangent, force towards the center. So in every position, the angle between force and displacement is 90 degree. So the work done by centripetal force is 0. So here you can see centripetal force F and displacement S are perpendicular to each other. So no work is done by this force. And a very good example, no work is done when Earth revolves around the Sun. For that matter, no work is done when the Moon revolves around the Earth. Moon M is revolving around the Earth. No work is done. So, a force displacement graph, important graph. So, if you take force on y-axis and displacement on x-axis, for constant force, you will get a horizontal line like this. Force is constant. And if you want to find out work done between any two positions, you see, then see this side is F and this side is X, and work done is force into displacement, length into breadth. This is going to be area. So the work done is given by the area under the force displacement graph for constant force. Let's see what happens if the force is variable. So this is a case of variable force. We want to find out work done between any two displacements like these two. We want to find out work done between this position and this position. And what we do is we divide the whole displacement into very thin strips, right? And when the strips are very thin, say dx, and this is force, then force into displacement, length into breadth will give area of this thin strip. So area of the strip will give you work done, और ऐसे जितने thin strips होंगे उन सबको ऐड करके आपको total work done मिल जाएगा as area under this graph. So let's see what happens. Okay. So if you take a thin strip like this, the work done dW is given by this area. Just assume that this strip is very, very thin and the thickness of the strip is dx. And the total work done will be sum of all such work dones. So dW is FDX. And see. So the work done is area under Fx graph, force displacement graph. So very important outcome of these graphs. You should be able to calculate work done from force displacement graph. Now work energy theorem, very important theorem, and let us do it for constant force. So here we have a body of mass m moving with some initial velocity u, and then some force F is applied on it. So its velocity increases to it undergoes some displacement s, and then its velocity increases to v. So we want to find out work done. So when a body of mass m is moving with initial velocity u and a constant force F is applied on it, which changes its velocity to v after displacement s, then we will use these relations. So work done by force is force into displacement. Let it be equation number 1. And let us use third equation of motion. So to find out displacement, you see displacement S को आप एक साइड रखो, इस 2a को दूसरी साइड ले जाओ. So S becomes v square minus u square upon 2a, and put this value of S in equation number 1. So what we get now is, see, from equation 1, work done W is equal to force into displacement, and you know that force is equal to ma, F is equal to ma. Use S from this equation. So v square minus u square upon 2a, and here we can cancel this a is cancelled, and then we can keep 1 upon 2m outside bracket, and inside bracket we get this whole thing, v square minus u square. Okay? And now left side is work done, open the bracket, right side becomes half mv square minus half mvu square. Now this is final kinetic energy, this is initial kinetic energy. So this is equal to kinetic energy final minus kinetic energy initial, or change in kinetic energy. So we can say that work done is equal to change in kinetic energy, and this is statement of work energy theorem. So see, work done by a force on a body is equal to change in its kinetic energy. This is statement of work energy theorem, and the derivation is meant for constant force. Now we can derive the same relation for variable force also. So for variable force, some integration will be involved here. So work done is f dx, small work done we have done that, dw is equal to f dot dx. So to find out total work done, you have to integrate both the sides. So जब integration आप करेंगे, so the work done is f dx, और यहाँ पर जो भी आपका आएगा dx, उसकी लिमिट्स इधर आ जाती हैं. So lower limit x1, upper limit x2, displacement from x1 to x2. And now put f is equal to ma, and then you can write a acceleration as dv upon dt. Acceleration is rate of change of velocity. Okay, and now at this place we take some adjustments. Now I can write this dx upon dt together and dv separated. So from here let us come to this one. So the work done is m dx upon dt dv. अब यहाँ पर जो भी आता है, यहाँ पर हमें उसकी लिमिट्स वही रखनी होती है. सो सिंस dv कम्स हियर, वेलोसिटी है तो इनिशियल वेलोसिटी u to final velocity v, lower limit to upper limit, and dx upon dt is velocity v. So this becomes integration u to v m v dv, and m is constant, mass is constant, so take it outside, and inside integration we get v dv. And you know relation for integration, you know that integration of x to the power n dx is equal to, say, power increases by 1, n plus 1, x raised to the power n plus 1 divided by n plus 1, right? So using this relation, now I can write work done is equal to m outside as it is. This here power n is equal to 1, you see, this n is equal to 1 here. So power increases by 1, v square upon 2. Now this 2 is constant, so constant भी आपने बाहर निकाल लिया, आपको मिलेगा half m. और limits, once you use the formula, आप limits right side में लिख देते हैं. So यहाँ पर lower limit u, upper limit v, and inside bracket now upper limit minus lower limit, v square minus u square. And now open the bracket. So the work done W is equal to half mv square minus half mu square. This is final kinetic energy, Ke final. This is initial kinetic energy, K is initial. So final kinetic energy minus initial kinetic energy is change in kinetic energy. So we arrive at work done is equal to change in kinetic energy, or work done by a force on a body is equal to change in its kinetic energy, work energy theorem. So we have proved this work energy theorem for constant force as well as variable force. It is applicable everywhere. So let us move to power. So power is rate of doing work, and power means work done per unit time. If delta W is work done in time delta T, power is work done upon time taken, and power is a scalar quantity. Its SI unit is watt, and then 1 watt will be equal to 1 joule per second. Dimension of power is this, ml2t minus 3. And another form of power is this one. See, if we take differential form, then power is rate of doing work dw by dt. Now dw is force F dot dx displacement, and displacement per unit time dx upon dt is velocity v. So here we have a new relation for power, that is power is scalar product of force and velocity, or this is equal to Fv cos theta, where theta is angle between vector F and velocity v, right? And now based on this we are going to solve a very good numerical problem. So let's see what it is. A 10 kilogram mass is moving up a frictionless inclined plane with constant velocity of 2 meter per second. The inclination of the plane is 2 in 20. Acceleration due to gravity is given. You have to calculate the power required, and you have to find out the work done in 5 minutes. So let's see. Let this be the inclined plane at an angle theta, and according to the question the inclination is 2 in 20. So when we say inclination 2 in 20, it means when you move 20 meters up the inclined plane, its vertical height becomes 2. So from here, if we have this mass m, then its weight will act vertically downwards, and its component down the inclined plane is mg sine theta. See, if this angle is theta, then this will be 90 minus theta, and then component down the inclined plane will be mg sine theta, and it has to move upwards. So the applied force F is upwards, and it is moving with constant velocity v. So now the body is moving upwards, so let us find out the net upward force acting on it. So see, the net force up the inclined plane is F minus mg sine theta. You see that? See, the upward force is F, downward force is mg sine theta. So net upward force will be this F minus mg sine theta. So, and this force should be equal to ma. Now a is acceleration, and since velocity v is constant, acceleration a is 0, so this becomes 0. So that means F is equal to mg sine theta. Now we can find out this mg sine theta. Now mass is 10 kilogram, g is given to be 10, and sine theta is 2 upon 20. For this inclined plane, this sine theta is height 2 upon hypotenuse 20. So sine theta is 2 upon 20, and from here when you simplify, you get 10 Newton, and power is F dot V, and force and velocity are along the same direction, so it is Fv. So force is 10, velocity is given to be 2 meter per second. So the power used is 20 watt. So power applied is 20 watt, and work done in 5 minutes is, now work done will be power into time. So power is 20 watt, time is 5 second. 5 minute, so convert it to second. So 5 minute into 60 second, and from here when you multiply you get this much as work done. So in this way we can calculate, we can find out work done and power acting on a body. So with this I come to the end of this video. I hope that it is useful to all of you. Thank you for watching it.